In what I hope is the last screencast on circles, we're going to look at two ideas, one of which we'll follow up later on for other curves, one of which is a very simple idea. So for the first one, we're going to see how we can determine what's called the equation of the chord of contact, or sometimes called the polar line. So in this diagram we've got a circle, and I've taken a general circle which is the form shown here, again with the usual centre and radius, centre minus f minus g, radius f squared plus g squared minus c, all square rooted. Now we don't need to know either the radius or the centre particularly to solve this problem. The question is this: given a circle, so you know F, G and C, and given a point outside the circle, which I've labelled as T, with coordinates H and K, can I write down the equation of the straight line which passes through the two tangency points at the circle, labelled here P2 and P3, whereby I mean the 2 points that you get when you draw the tangents from T to the circle. So can I explicitly write down the equation of the straight line through P2, P3? Well, you could probably work quite hard to generate all straight lines that pass through T, see where they intersect the circle, insist that they intersect only once, so it's a tangent, but of course you'll have two of them, then define the coordinates of the tangency points and then determine the straight line through the two. That's extraordinarily tedious, and there's a much easier way of doing it. So here goes. So we only know the equation of the circle, which is this, and we know the coordinates of the point T. Now, let us suppose that the two tangents that we draw through T touch the circle at 2 points, P2, P3, with the coordinates labelled. Now, immediately we can use the expression from the previous result, which is on the previous page, or 2, which says that the equation of the tangent to that circle at the point x1, y1 is given by this. Well, if we're assuming that the 2 points, the two tangency points are P2 and P3, which we don't know and we don't particularly want to work them out, we can at least write down the equation of the tangent to the circle at the point x2, y2. It's given by this expression here. And that's just by taking that previous equation of the tangent and replacing x1 and y1 by x2, y2. Similarly, for the other tangent, we can take that same equation and replace x1, y1 by x3, y3, and we get this. So these two equations represent the two tangents shown. Now what I'm after is the equation of the straight line that passes through P2, P3. So let's take those same two equations. So these two equations represent the straight lines which are the tangents that happen to go through T, but they're the two tangents to the circle from that point T at those two pairs of coordinates, x2, y2, x3, y3. But because those two tangents pass through HK, then these two equations are satisfied by the coordinates h, k. So I can substitute in here for x and y as h and k, and what I get is still true. This is just stating the fact that the two tangents must pass through HK. Now if you look very closely at these two equations, what you notice is that what they have in common are the h's, k's, f's, h's, k's, c's and the g, but that one's got x2, y2 in and one's got x3, y3 in. But obviously from these two expressions we can see that this straight line is satisfied by both points x2, y2, x3, y3, because if I substitute into this equation x2, y2, then this expression from here is 0, and hence this is 0, and hence x2, y2 lies on this line. And similarly x3, y3 lies on this line, so that's easy to verify. Why did I write down this straight line? Well, I noticed that if I took those two expressions and wrote down the straight line where I just replaced x2, y2 and x3, y3 by x and y, which is this, that x2, y2, x3, y3 automatically satisfy this. But of course this is the equation of a straight line. It's the equation of the straight line which we've just established passes through x2, y2, x3, y3. In other words, it passes through p2, p3. So I've got the equation of the straight line that passes through p2, p3. It's that. And that is the equation of the polar line or the chord of contact. It's the equation of the straight line that passes through those two tangency points. And obviously it only depends on F, G, C and the point T. The remark here just says that the equation of the polar line, which is this, that chord of contact, looks very similar to the equation for the tangent at the point x1, y1, where you just replace x1, y1 by h and k. They represent different things, but they look exactly the same in the two different contexts. So lastly, if we're given 2 points in the plane, can we determine the circle that has the line segment between those two as a diameter? Well, we could write down the general equation for a circle and insist that it passed through those 2 points. We could make sure that it was a diameter, so it's the largest length between the two. But the simplest way of doing this is to note that if I draw the circle that passes through the 2 given points A and A dashed, and insist that A dashed is a diameter, then if you take any point on the circle, it subtends a right angle at the diameter. In other words, for any point P, A dashed P and AP are perpendicular. Well, of course, if we write down the gradient of the line segment from A dash to P, which is this expression, and the gradient of the line segment from A to P, which is this expression, then because those two gradients are of lines that are perpendicular to one another, their product must be -1. So these two have a product which is -1, and if you multiply those together, set them to be -1 and rearrange, you get the boxed equation. And you can see that it's got x squareds and y squareds and x terms and y terms and a constant term. So it's certainly a candidate for being a circle. It's got the same coefficient of x squared as it has y squared. They're both 1. So it's going to be a circle so long as it's got a radius, or so long as h and k are not the same points as h dash k dash it will have. So this is a very neat form determined by a little bit of geometry for the equation of the circle, whose diameter it will be at the ends of 2 given points A and A dashed.